First of all, John, thanks for taking the time to speak to us and welcome to Northwestern University. This is a school-wide lecture series, and we are delighted that you're taking the time to chat with all of us. So I'll quickly introduce John and then turn the floor over to him for his lecture. So John got his undergraduate degree at Cornell University, and then he got his PhD at MIT in the mid-90s. He started off his research mainly working on graph theory, graph algorithms, theoretical computer science, but very quickly, his interests branched out and he worked in a variety of areas: social networks, artificial intelligence, with a very broad applicability of algorithms and networks. He is currently the Tisch University Professor for Computer Science and Information Systems. He has a very, very long list of awards to his name. He's extremely accomplished, basically set the gold standard for theoreticians in computer science. He's a member of the National Academy of Sciences. He's a member of the National Academy of Engineering. He also received a MacArthur Genius Award, a Packard Research Fellowship, Sloan Fellowship, Simons Investigator Fellowship, Bush Vannevar Bush Award, the Nevelina Prize, and a whole host of awards in computer science. So I'm delighted that he's going to be able to talk to us today. And the topic of his lecture is fairness and bias in algorithm decision making. And for questions during the talk, I suggest that you post them to the chat box. And then right around 12:45 when his lecture ends, I'll go over the questions in the time that we have and ask those. So thank you all for attending and turn the floor over to John.
Okay, well, thanks. Thanks very much. I'll switch over to screen sharing, and assuming everyone sees the slides, that should be working. So thanks very much for the invitation to take part in this lecture series, and I'm happy it works out to do it in this virtual format. My talk will be about some issues that have been very active in the algorithms, machine learning, data science communities over the past few years, related to questions about fairness and bias in algorithmic predictions. The particular slice of work I'll be talking about is joint research with three collaborators: Jens Ludwig, Sendel Mulleinathan, and Cass Sunstein. And we come from four different areas collectively. I'm coming from computer science, Jens from public policy, Sendel from behavioral economics, and Cass from law. And in some sense, my interest in these topics began over roughly the past eight years through a series of lines of work that Sendel Mulleinathan and I have been doing. We had known each other for a long time, but we discovered over the past decade or so that our interests in computing and in behavioral science, respectively, had begun to converge around this topic of prediction and evaluation. And so I thought I would start just by suggesting some of the reasons why these things started to come into alignment. So if you think about the kind of problem that computer science has become very good at solving, one category of these are recommendation and ranking problems. So this is a screenshot of a help page from Netflix, and effectively it's explaining, sort of in very rough terms, how they go about estimating the probability that you will like some movie, such as this one pictured here, right? And so we take some past features about you, right? You have some complicated actual collection of tastes and interests. We reduce that down to a feature vector, a much sort of low signal representation based on your past viewing habits. We look at other people, and based on that, we make a prediction of the probability that you'll like this movie. And what Sendel and I began to notice was that this kind of problem in stylized form was also being solved in the offline world, and has been for a long time, right? When you apply for a job, for example, you submit a resume to a prospective employer, and in some sense, something fairly similar is happening. We take your complex past work experiences and educational experiences, we reduce them to a tabular collection of features encoded in the resume. It gets passed now not to a recommendation algorithm, but instead to a human hiring committee that looks at this resume and tries to predict something. What exactly they're predicting is actually sort of complicated to try figuring out. In some sense, that's going to be part of the point of the talk. But at some level, they're trying to make some estimate of you from these features, much as the recommendation engine was. A similar thing happens with college applications. A student takes their K through 12 experience, reduces it to a feature vector, and somebody is trying to make some sort of a prediction about their future performance. So all of these could be viewed as what you might call screening problems, where people come into a setting, there are some features about them, and they all follow this pipeline pictured here on the slide. The features get passed through some decision maker, be it algorithmic or human, and out comes some prediction. Do they have a high probability or a low probability of engaging in some future thing? Liking a movie, being a good employee, being a good college student. And we see similar things with, for example, allocation of credit, or with criminal justice, for example, where at pretrial hearings, a judge may be trying to predict probabilities of future reoffense. Now, this was sort of in a sense where this, I think, the computer science community's interest in the idea of fairness and prediction sort of took off from, because, people began saying, if our techniques are so effective in the online world for things like movie recommendations or search engine rankings, and if the offline world is filled with prediction problems in employment and education and credit and so forth, maybe some of our techniques would be relevant there. Maybe we can help people make better predictions using algorithms. But these kinds of questions are what you might call high stakes decisions, right? High stakes because in the end, it doesn't really matter whether you like that movie or not. But it matters a lot for somebody whether they get this job they applied for, whether they get into college, whether they wait for trial in jail or out in the community in the case of recidivism prediction, right? Individual decisions here matter a lot. This is, of course, not to say that the online domain is, inherently low stakes. After all, if I take decisions, for example, about which news articles to show you, and I repeat that 100 billion times across the whole population, then we get something very high stakes, such as the formation of public opinion and its influence on elections. But those domains are individually low stakes. No one decision is mattering, whereas here, individual decisions are mattering a lot. And because of that, we begin to have questions about the risks of bias coming to decisions for both human and algorithmic decisions. Now, for human decisions, the risk of bias is something that's been studied for a long time. And what's been intriguing here is the ways in which algorithmic bias both partly resembles, but is partly distinct from human bias. So in order to talk about that contrast, I should first briefly talk about some things we know about human bias. So there's a long line of empirical work on this. It, in a sense, gathered a lot of momentum in the 1990s with empirical research on implicit and also explicit bias in human evaluations and human judgments, and on how we might audit the effects of that bias. So to take one example of some now classical empirical work done in the 1990s, in this case by two social scientists, Christine Veneras and Agnes Vold, they produced this plot on the right-hand side of the slide here. What they did was they, in a kind of study that we see a lot of varieties of, they actually went to European Research Commission grant proposals. And when these proposals get submitted, there's a component of the evaluation in which the reviewers evaluate what's called the sort of competence of the PI. They assign a competence score. And that's a subjective evaluation based on the credentials of the PI. Now, Veneras and Vold were interested in the question of, are women being systematically assigned different competence scores than men for roughly comparable levels of past achievement? And so they went through and created many, many different notions of past achievement, number of citations, number of high impact papers, papers in top venues, past funding history, and lots of notions of impact. And they plotted this impact on the x-axis here. And sort of for all the different ways they could think of to create notions of impact, well, what we see here proved to be quite robust, that for a fixed level of total impact, say this 40 to 59 range, the average competence score being assigned subjectively by reviewers to men applying for grants was significantly higher than for women. And in effect, in order to get the same competence score for women researchers, you had to have much, much higher in these objective measures of impact. And this was a finding that began to emerge in many, many different domains, that these subjective evaluations seem to have these inherent biases that broke down along groups that were quite recognizable. there were these interesting questions about potential confounds in this. After all, you know, men and women may work in slightly different areas. These notions of impact might not mean what we think they mean. But in some sense, the sort of the final word on this was through a now famous study that my co-author Senthil Mullainathan did with Marion Bertrand shortly after he finished his PhD in the early 2000s. What they did was they said, okay, let's control for all of that by simply taking resumes, sending them out to employers, and simply changing the name at the top of the resume, keeping everything else identical. And so going through the US Census, they found names that statistically were associated with people who were white and people who were African American. And presumably employers looking at the resumes would have those same associations. And so they sent out these identical resumes and then waited for, these were completely fictitious resumes, and waited for employers to call back requesting for interviews. And the callback rate, the interest expressed in interviews, went down by a factor of roughly 2/3 when the name at the top was statistically African American. Right? In other words, simply changing the name at the top had this huge impact, keeping everything else the same. And you know, this has now become one of the more replicated studies in the social sciences over the past 25 years. It's unfortunately an extremely robust finding, and it says that there is this sort of human bias that pervades these screening problems in a very widespread way. So this is sort of the backdrop on human bias that we have to think about when we start thinking about algorithms coming into these domains and trying to make screening decisions. Now, what's interesting, let's go back to this pipeline that an algorithm, you know, might be used in, where an individual gets mapped to a feature vector, passed through a decision maker that may now be an algorithm, and out comes a prediction, such as the hiring committees were making, perhaps, such as the reviewers of ERC grant proposals were making. Now, algorithms, of course, it goes without saying, have no direct incentive to exhibit bias. They're simply trying to optimize some objective function that you gave them. Despite this, and this is sort of the key point to emerge out of the past 8 to 10 years of research in this area, is that despite this, there are many potential sources of bias in algorithms. Where are some of these sources of bias coming from? Well, so these features over here on the left is one, right? So for example, perhaps the features I feed the algorithm are the competence scores that we saw on the previous slide that were assigned by human evaluators. Maybe that's one of the features. But that, of course, reflects the bias that we already know is in there, and therefore that bias is now being passed into the algorithm, making its decisions. Similarly, if we move over here onto the right, there could be bias in the choice of objective functions, right? So perhaps I'm training an algorithm to select employees who are going to get good evaluations on their proposals. But we've just learned that proposals have biased evaluations. And so by the algorithm trying to optimize for that, it may be trying to optimize for people who will do well in this biased environment. And that actually, in a sense, reproduces the bias as well. And we may have bias, for example, in just the procedure used to train, right? I have to collect training data, and unless I'm careful in trying to sample from the full distribution of instances, I may end up with it that way also. So there's this interesting thing going on here, which is if we're trying to look at where bias might be creeping into an algorithm, it somehow means that we need to be understanding things about how that algorithm is constructed, how it's operating. And so we run into the problem that algorithms are, of course, becoming increasingly complicated. Often machine learning algorithms trained on large amounts of data, particularly so. And people have wrestled with the challenge of interpreting algorithms, right? So the problem of interpretability of these algorithms has become an important question in its own right. But there's clearly a linkage, as we see, between these two topics, right? Between the fairness of algorithms, the potential for bias, and the interpretability of algorithms, our ability to probe them to figure out what they're doing. And so one thing that I want to think about here is how these connections might work between our ability to interpret algorithms and our ability to audit them for bias. Now, it's interesting that if we go back to human decision-making, because there's always this interplay, right? The algorithmic bias is really picked up from the human environment that they're operating in. The legal frameworks about human bias, and for example, discrimination law in the US, also has some notion of interpretability in it. The question of understanding why people made the decisions that they made. And we can see that, in fact, in the distinction between the two main categories of discrimination that the law recognizes, disparate treatment and disparate impact. So disparate treatment is the category of discrimination in which someone making a screening decision, such as in employment, is deliberately favoring certain candidates on the basis of protected attributes, such as race, gender, national origin, religion, age, or any of a host of other properties. So a claim of disparate treatment requires that you actually somehow uncover the fact that the person making this decision actually had a preference, was expressing it, was engaging in a preference based on one of these protected attributes. That's often extremely hard to figure out. And so there's a second category of discrimination, which is also legally challengeable, and that's disparate impact. Disparate impact says that regardless of the decision maker's intent, if the screening decision has a disproportionate and adverse effect on a protected group, then it becomes suspect. And then the burden shifts to the decision maker to establish so-called business necessity for this disparate impact. Thus, for example, if you are hiring for a job that requires people to be extremely tall, because it's a job that's based on reaching things that are in extremely high up places, then you might say we need to have height be a criterion, even if height has a disproportionate impact on certain categories of applicants. On the other hand, if I'm hiring, say, software engineers and I made height one of my criteria, it would be very hard to justify that on the grounds of business necessity. Okay, so this is how we think about adverse impacts and discrimination. We're talking about human decision making, and the point is that it can be very hard to tell if a human decision maker has actually engaged in one of these types of discrimination. Disparate treatment, because we'd have to know whether they had this preference. Even disparate impact, because we'd have to know their rationale, their genuine criteria for making these decisions. And the problem is not just that people being accused of discrimination might lie. There's a deeper problem going on, which is really a sort of very deep point that's emerged again from the past 20, 30 years of behavioral science research, that people, even when they're trying to cooperate with you, even when they're trying to help you, they might genuinely not know their rationale. This is something which is now, becoming increasingly well understood in the psychology literature. It dates back to a different series of now classic experiments, including a series of experiments by Nisbet and Wilson, which asked subjects to make choices and then to explain their choices, where the experimenters introduced a confounder that was known to them but hidden to the subjects. And let me explain how one of these works, for example. So I bring people into the lab and I give them a word memorization task. I ask them to memorize a whole bunch of words. And then I ask them to name a product, say, name a brand of laundry detergent, and they name something. In group A, I do that with random words. In group B, I do exactly the same thing, but I ask them to memorize words like beach, ocean, sand, moon, waves, and then I ask them to name a brand of laundry detergent, and many, many more of them say Tide, right? That's something that is well understood. It's a priming effect. I get you to think of a lot of words proximate to the word I want you to think of. I've primed you, and now you say it. But they went one extra step, and they did the following interesting thing. They asked people, why did you pick this particular brand of laundry detergent? And people would say, because it's the one I use, my family used when I was growing up. It's the one that I use now. I remember the logo, I see it in the store, all sorts of things. Almost no one said, because you primed me with all these hidden words, right? So there's a giant difference between group A and group B in how many people say Tide. But when you ask people, why did you say it? They retrofit all of these explanations, even though we know there was a reason that none of them have uncovered, right? So this is sort of a key point about human explanations. And in some sense, an important point about interpretability. We think of algorithms as black boxes that we have a very hard time figuring out what they're doing. Whereas humans often give us the illusion of providing an explanation. They're happy to tell you why they did something. But the challenge is that may be just that. It may be partly an illusion. That may not be the real reason why they made these kinds of decisions. There is a long line of experiments of this form. In another example, Nisbet and Wilson asked people to choose their favorite article of clothing from a rack of clothes, but oriented in a way so that they could induce a strong bias favoring the right-hand end of the rack over the left hand. Again, no one noticed this, and so they gave all sorts of reasons why they chose a particular article of clothing, not realizing that the answer had sort of been almost forced on them. Okay, so this is sort of a key argument that we could then make, and that in this joint work with Jens, Sendel, and Cass, that we do make, that something interesting changes when we start using algorithms for screening decisions. Yes, there's a danger of bias from the human environment that they're embedded in, and that's the core challenge. But on the other hand, an orthogonal dimension emerges. It's entirely possible that well-regulated algorithms may make discrimination easier to detect. Because whereas humans are these black boxes who may try to give you explanations, but may not succeed, with algorithms, there's a sense in which, even though they're very complicated, certain things are explicit in a way that they just can never be with human beings. Now, when I think about algorithms here, it's sort of important to sort of pop up and sort of say something that I think, is familiar to all computer scientists, that when we talk about machine learning prediction algorithms, we're really talking about two algorithms. There's a training algorithm, which takes the training data and produces a classification rule. And then there's the classification rule itself, the screening rule that gets applied. Right, so the trainer is really an algorithm that produces as output algorithms, classification rules. The classifier takes actual instances of, say, job applicants and outputs yes, no decisions. And we could think about sort of where, how both of these work and how we might probe them in ways that we could never probe a human being with a level of explicitness that we could never have hoped for in these offline processes. Now, this is not to say that we can read the code and expect to understand how the algorithm is working. We certainly can't do that. But we can do a number of other things, right? If we have requirements that the process by which the algorithm was constructed have been made explicit, and if the process followed the standard machine learning pipeline, then we can, for example, examine the features that went into the algorithm. We can ask for the choice of objective function, right? We can go and take all of that and build our own screening rule and see if we get the same level of bias that was happening in these cases. Think how hard this is to do with a human being, right? I could take a human hiring committee and I could ask them, what was your criterion for evaluating applicants? And they might attempt to tell you, but it would never be the level of explicitness that you would have with an explicit objective function embedded in the algorithm. Similarly, I could take the classification rule that comes out and I could ask the question, this job applicant was female. Would the decision have been the same had this job applicant been male? I could flip the bit, pass it through that same classification rule. In other words, I can create synthetic instances, and I can actually get the algorithm to answer me on those synthetic instances. This too is something that you could ask human beings this, but you could never hope to get a sort of plausible answer, right? I could ask somebody, if this person had been exactly the same but slightly different, would you have done the same thing? And it's just simply not possible to ask that question with the level of concreteness that I can in the case of an algorithm. Now, note that all of this has this important adjective, well-regulated algorithm. It's key in all of this that there be record-keeping requirements, that the features that were used, the training data, the objective function, all be recorded and available for examination in the case of a claim of discrimination. That's not the state that the world is in now. And so this is not a statement that the world as it's constructed now is necessarily amenable to this kind of auditing, but that this may be an aspirational goal that we might want to get to. In a world where people keep algorithms secret, then you essentially can have situations where you now have an actor who may have bad intent, and now they have a powerful tool at their disposal, a secret algorithm. That only makes things more dangerous. So it's crucial that all of this would work in the event that we can actually examine all of these things. You may say that's a huge amount of record keeping, but it's important to note that in other regulated areas, record keeping requirements are often quite extensive. In financial markets, for example, requiring that all transactions be recorded is extremely expensive and extremely onerous on firms, yet we do it because we believe that the value is correspondingly high. That effectively is what we could consider doing in the case of algorithms engaged in these screening decisions. So I want to talk about a bit how this would work in sort of increasing amount of technical detail. What would it mean to audit an algorithm for disparate impact? And as a first step, I wanted to go back to something which I said informally at the beginning and see if we can make it slightly more formal. When I was talking about the potential sources of bias in the algorithm, I mentioned, there's a potential bias in the choice of label or the objective function. There's potential bias in the features that we use. And there's potential bias in the training data procedure. For example, if we use non-representative training data. And when we were first doing this work, we talked about these three as a kind of cluster of attributes. And naturally, I began to worry, is this all of them? What if there's a fourth one? What if this is only 3 out of 7 ways bias can come into an algorithm? Is there even any sense in which we could try to formalize that these are the 3 categories that we should be watching out for? And it turns out if you write things down carefully, there's a sense in which you can say something like that. So let me suggest a model for screening decisions that I'll sort of use for a bunch of the discussion that follows, in which I imagine that I have individuals who are applying for something. Let's imagine for a job or for college admissions. Each individual has a feature vector X, and there's some function on which I'm ranking people. Let's call that the productivity function. Again, so it's whatever it is I actually care about in making my selection, right? There's some reason I'm doing the screen decision. And it's a function of the features. Now, I'm concerned about discrimination. So let's imagine that there are 2 groups. I'm just concerned with discrimination between them. So there's an advantage group A and a disadvantage group D. In what sense is group A advantaged? Well, the feature vector X, let's imagine, doesn't actually include group membership. It's really just everything I need to know about the person to make this decision. And if I knew everything in X, I wouldn't actually care about whether they're in group A or group D. Nonetheless, group A is advantaged because they have an abundance of feature vectors that tend to produce higher productivity values. Right? So imagine that the feature vectors include things about your level of K through 12 preparation. If you're in an advantage group, you grew up in a neighborhood that had more well-funded schools, you had more K through 12 preparation. And so as a result, the distribution of feature vectors in group A is skewed toward X's that produce high values of the function F. That produces a disparity. So one way to write down this disparity is in this last bullet here. Let's say for any function V that I'm interested in, maybe F or maybe something else, the disparity in V is the weighted average of F values in group A. That's just the sum over everybody in X who's in all possible feature vectors of their abundance in group A times the value, minus the weighted average of values in group D. Okay. So for example, if I plug in F here, then I have the weighted average of F over A minus the weighted average of F over D. That's what social scientists would often call the structural disadvantage between the groups, right? It's the disadvantage experienced by group D based on the allocation of feature vectors producing differences in productivity. So structural disadvantage is something that predates the decision being made by the screening algorithm or by the decision maker. That's gonna be something that's gonna be present even if you were careful not to add any extra discrimination in. That's the discrimination that was that was the disparity that was already present. Discrimination is effectively about attributing additional gaps to something you did in your decision. Now, how can we do things that would widen the gap? Well, consider all the things that we do when we design an algorithm, and I'll list them in these four bullets here. We start with the structural disadvantage, but then we don't necessarily use F, because F's some very complicated function that's, in a sense, unknowable to us. So we instead, in building the algorithm, create some other function, G. Similarly, the full set of features is enormous, and many of them may be unmeasurable. So we use some reduced representation. Instead of the full X, we use some reduced vector R of X. Now, there's sort of a type checking thing here, because I can't plug R of X into G. G is some enormous function that expects an enormous vector. So I need to have some shrunken function. Let's call that H. So that means instead of evaluating G of X, I'm evaluating this composition. I first do R of X, then I apply H to it. So I have H composed with R. And finally, of course, I can't really get my hands on H because I only have some training data, and I'm trying to induce something from the training data. So I run a training procedure, and instead of producing H composed with R, it produces some trained rule T composed with R. And finally, the end of the machine learning pipeline is really T composed with R. Right? So this is sort of step by step how we end up with a trained function running on a reduced feature representation. Now let's think about what that does to the gap. And there's a very simple, let's call it a telescoping sum in a sense, that says the disparate impact I'm going to get from my decision rules, this thing over here on the left, the disparity in T composed with R, the thing that I produced. But I could write that in the following sort of deliberately expansive way. It's the structural disadvantage, D of F, plus D of G minus D of F, plus D of H composed with R minus D of G, plus finally D of T composed with R minus D of H. Right? And that's just arithmetically, a whole bunch of these terms all cancel out, and I'm left with D of T composed with R. But the way I've chosen to write it highlights that it consists of 4 terms. The structural disadvantage, followed by d of g minus d of f is the extra gap introduced because I chose to specify the outcome differently. This next term is the bias that came in, the extra gap, because of my choice of features. I was using the reduced representation, not the full one. And finally, the gap from the bias in the training procedure. And so as a result, it actually, in a way, makes precise the idea that this really is all of the places where this gap can come from, added on to the structural disadvantage. And so if we have an ability to examine the pipeline, we may be able to then try identifying these places where potential discrimination was introduced. So this is making the argument that using algorithms allows us to audit processes in ways that we could never do with human beings, right? Human beings come with this nice sort of engagement with us where they try to explain their decisions, but they might be wrong. Even with the best of intentions, they might be wrong. And so when we evaluate claims of discrimination, where we have to attribute a gap to different components of the decision, algorithms contain ingredients that actually make this possible, provided we have regulations in place that allow us to examine. And to come back to this point, all of these really rely on being able to investigate algorithms, being able to interpret what they're doing, a form of interpretability. It doesn't require us to read the code again, right? All of this is about probing the process by which they were constructed, being able to ask counterfactuals, being able to almost experiment with them as natural objects. Because obviously we know, for all sorts of reasons, both our own cognitive limitations as well as the theory of undecidability, we're not going to read the code and understand, but we're going to be able to do other things. So given this close connection between our ability to interpret algorithms and fairness, we want to go on, and Sendel and I try to look more deeply at this question. What are the sort of deeper connections between interpretability on the one hand and fairness on the other? And we found some interesting things here, which is that there's a sense in which our efforts to make algorithms more interpretable, to simplify them, to increase their comprehensibility to us, may in some cases actually work at odds with the fairness properties of them in ways that may initially seem counterintuitive, but sort of make sense as we look at them. So I want to run through that argument at a high level. And to run through that argument, I'll come back to the model that I was just using. Again, let's imagine applicants to a job, for example, where I'm going to try hiring a sort of the top subset of them. So applicants are described by a feature vector. And let me be a little more explicit. It's, say, a feature vector with a bunch of Boolean variables, though it's not crucial they be Boolean. And I have my productivity function, which is a function of these features. And my plan is to simply take all the applicants, sort them by their F value, and I have some admission rate R. I'm just going to take the top R fraction and admit all of them, right? Accept them to college, hire them for a job, whatever. Okay. Again, group membership, you can be in the advantage group or the disadvantage group, as before. And again, crucially, the function F is independent of your group membership. If I told you all of X, you wouldn't care if they were in group A or group D, because you would have the information that you needed. You'd have f of x. Nonetheless, group D is disadvantaged because the distribution of features is such that features leading to higher values of f are overrepresented in group A, right? That's the key point. The values that give you high values of f are more prevalent in the advantage group. And let's express this using what I'll call a likelihood ratio condition, which is that if I look at an x and an x prime, and x is a better feature vector in the sense that it gives me a higher value of f, then its relative prevalence in group A is correspondingly higher than the prevalence of x prime. Okay, that's the likelihood ratio condition. Better x's are more overrepresented in group A. All right, let me run through an example, like extremely concrete example, so that we can sort of see how this, how this works. This is an example, obviously, of an extremely simple function. So, in reality, there'd be no problems working with this function just by hand. But so as to be able to do it on a slide in real time and we all process it, I'm picking a deliberately simple function. Let's imagine I have two features, x1, x2. They're both Boolean. And the true criterion is just a conjunction of them. So a good employee is one for whom both of those things are equal to 1. Here's how they're distributed in the population. If you're in group A, then you have each xi set independently to 1 with probably 2/3. Right? So you have the good feature with probably 2/3 independent. And if you're from group D, you have it set to the good value independently, but only with probably 1/3. That's the sense in which group D is disadvantaged. So we end up with this truth table. The truth table says, here are all the choices for x1, x2 in group membership. Here's the F value, and here's the relative fraction of that in the population, the relative abundance. Say the two groups have equal sizes. Right? So if you're in group D, then having x1 equal to x2, that's a 1/9 probability, and you're half the population, so it's 1/18. Good. So that's fine. And so that means that if I actually had access to this function perfectly, then 5/18 of the world has the good value of f, right? So at all admission rates are, all small admission rates are less equal to 5/18, all the admitted people would have f value equal to 1, the highest possible. But only a 1/5 fraction would come from group D. So we see how the disadvantage in distribution turns into disadvantage in this decision rule, just purely through the structural disadvantage. Okay, now let's suppose we want to simplify this function, right? We'd like to make it more interpretable by somehow reducing its complexity. And one way we could do that is to use only x1, not x2. Again, with a complicated function with hundreds of features, the process of simplification becomes correspondingly more complicated. In my simple example, simplification, let's imagine, just involves projecting out x2. Why would we project out a variable? Maybe it's too expensive to collect. Maybe we're doing it for this sort of argument of interpretability. A big reason might be, again, if we have a thing with hundreds of features, that for out-of-sample generalization, the principle of regularization argues that by simplifying the function, we can actually improve out-of-sample fit. Many reasons that we might be doing it. What effect would that have? Well, so we then have what I could call an F approximator, right? It's not the full truth table. It's the truth table where I've compressed rows into kind of aggregate averages. I get this truth table over here on the left, where I only care about the value of x1. x2 could be anything. The group could be anything. And now, notice what's happened. In an x value of 1, I have a whole mass of the population there that's indistinguishable to me because I don't know the other values. That's half the population. And their average F value is actually now 5/9, not 1. So now at all small admission rates, the average F value of the people I'm admitting is no longer 1, it's 5/9. I'm using a simplified rule, which is producing a less accurate fidelity on F. On the other hand, the fraction that comes from group D is now 1/3, not 1/5. So this is a trade-off that we often see in these situations. I've gained in equity. Now 1/3 of the population is from group D, but I've lost in efficiency. It's only 5/9. So that's a trade-off that simplification can have. We gain one thing, we lose another. But if you look a little deeper, it turns out there are some difficulties with this situation. And this example, in a sense, was sort of the jumping off point for us to try exploring some of the difficulties that come in when you start simplifying, not just losses in efficiency. Here's the first difficulty. Again, we have this F approximator on the right. Now, back when I had the full truth table, the big one with 8 rows, if you had asked me, would you, here's x1, x2, would you like to know the value of group membership? You would say, no, I don't care about the value of group membership. I have everything I need to know. Now, with this F approximator, let's suppose I go back and I ask the decision maker the same question. Would you like to know the value of group membership? They would say, why, yes. In fact, I actually would like to know the value of group membership. Because if I knew group membership, then I would actually potentially have the ability to use it. It may be illegal to use it, but I would have an incentive to use it because it's helping me recover a little bit of the missing value x2 through its correlation with group membership, right? Because if I created this expanding truth table where I knew x1 and I knew the group membership, now the average F value of the people in group A is 2/3. And the average F value of the people in group D is only 1/3. And so I'd actually improve my efficiency by using group membership, right? You may try to prevent it, but I would improve my efficiency. This did not happen with the original function. It happened only because we simplified it. It was this. So in other words, in sort of shorthand, simplification transformed disadvantage into bias. Where we once had structural disadvantage, we now have an incentive to have bias. This is actually something that we see in the behavioral sciences. In some sense, it's sort of this sort of simple mathematical level corresponds quite closely to mechanisms that are posited for stereotype formation in everyday life, right? In other words, when I'm missing information about somebody, I fall back on attributes like group membership as a proxy, or something where I attempt to fill in that information. We even see it in social policy applications in rather troubling ways. So let me tell you about one of those. There are these policies that were introduced a number of years ago called ban the box policies. So about the relation of criminal records to employment. So if you had if you were applying for a job, there'd potentially be a box in the job application, which you would check, to say, have you ever been convicted of a crime? Now, as part of an effort to reintegrate people who have returned from prison into the workforce, an argument was made, we should eliminate this question. We should not, employers should not be allowed to ask this question. So these were so-called ban-the-box policies because they want to eliminate this box from job applications. In some places, these went into effect, and a number of enterprising social scientists, including Amanda Agin and Sonia Starr, went and actually looked at the effect of this just before and just after the introduction of the policy. How they do this with things like the resume audit study that I described at the beginning of the talk, where you send out resumes and you simply change the name at the top. And what they found, quite troublingly, was that just after the introduction of ban-the-box policies, the gap in callback rates, right, the disparity in the name changes on resumes actually would jump. In other words, we can't say what any one employer was thinking, but in aggregate, employers appeared to be falling back on other attributes, group membership attributes, to fill in the information, this missing piece of information, right? Sort of an extremely troubling finding about the ways in which policies that sort of produce one effect can incentivize other pernicious effects. And so this is not to say whether, the takeaway is that ban-the-box policies, are, the pros and cons of them, simply to say that there can be these surprising effects where you create pernicious incentives through the elimination of information. And this really relates to this point that, we often think about, stereotype formation is particularly likely in cases of low information, cases where you're making decisions rapidly, without all of the facts that you need. We think of that as a very human kind of behavior. But what we're discovering here is that an 8-line truth table can engage in that also. If you take the 8-line truth table and you hide information from it, it too will have this pernicious incentive to fall back on attributes that you don't want it to use. There's a second point actually that comes up, which is simplification is not necessarily even the optimal trade-off between efficiency and equity. Let's again go back one more time to my simplified truth table here and say, imagine that I gave you the option to break out the people who had x1 equals x2 equals 1 who were in group D. I say, let's invest the money for members of group D to go collect that extra value of x2. Okay. Then I could create this new truth table where I have these people who have an average F value of 1. I select them first, and then I go and use the rest of this approximator as before. I've just sort of broken out one row of the truth table at the cost of extra resources. This has the property that it's better on efficiency, because I'm getting these people of average F value 1 first. And it's better on equity, because I'm admitting people from group D. In other words, it's a Pareto improvement on the original approximator. This is something where it says that the simplification wasn't even the best trade-off between efficiency and equity, because you can simultaneously improve on both. So the picture with simplification is actually quite complicated, right? And sort of in schematic kind of looks like this. I start with the complicated function. I simplify it, and I get to this unstable point in the landscape. In one case, I tumble down toward incentivized bias, where I get pernicious incentives to begin using group membership in a way that actually wasn't relevant when I had the full function. And in the other direction, I get Pareto improvement. This wasn't even the best trade-off between efficiency and equity. It's dominated in both dimensions. And so the general result that we're able to show is actually that this is a general feature. It's not just a feature of this example, but that, roughly speaking, for every Boolean function f with real valued outputs that satisfies this disadvantage condition and some sort of technical genericity assumptions I won't get into, and for every simplification of it, in which I take the truth table and I collapse rows into larger cells, replacing values with averages, then the two things I've shown you actually happen. One, that there's always Pareto improvement. There's always an approximator that strictly improves on my simplification in both efficiency and equity, essentially by strategically collecting extra information for certain groups. And two, there's always a pernicious incentive. If my approximator G does not use group membership, then adding group membership as a variable to it will simultaneously increase efficiency and reduce equity. Increasing efficiency, thereby creating incentive to use it, and reducing equity, thereby harming the disadvantaged group. Okay. Now, this only scratches the surface, I think, of the kinds of questions you can ask in the space of simplifications of functions in the space of interpretability. And so I just wanted to wrap up in a couple minutes with how I've been thinking about this. So simplification and the ability to understand algorithms is really part of this auditing pipeline that really helps us discover bias and discrimination in the process of algorithmic decision making. And as such, it's very important. But it also comes with risks, right? It comes with risks of creating these incentives and of not being an optimal thing. So I think there's a lot of interesting open questions here as we think about how interpretability and fairness operate. But I think the high level point really is that algorithms allow this sort of new level of concrete, explicit discussion about the decisions that we make and the biases that come into the process. They both allow us to think about our own human decision making, and they provide alternatives to human decision making that we can probe in ways that are simply really impossible with human beings. I think what's been intriguing here, and I think the joint work that we've been doing across a number of different areas has, I think been a sort of eye-opening for me, that many fields are going to need to play a role in setting these priorities. And I think there's in particular a lot of room for computing and applied math to have an important role in these conversations as an important contributor going forward. Thanks very much. Thanks very much for your attention, and I'm happy to take questions.
So I know many of the participants are muted and can't clap, but I'm very glad that so many people were able to join. So people should feel free to put their questions in the chat box. I'm going to open it up. So I had maybe a couple of quick questions for Jon first. One is that if somebody wants to learn more about this topic, is the good starting point like a paper or a survey or something that you can point us to that would be extremely useful? And then the second question I had with software, especially software that's developed by different parties, different companies that may be used. So just take an example: the government wants to make some decision about something, they put a bid out, and multiple companies compete to develop software for something. Now these companies might not want to reveal all of the inside details of what they were using. I mean, just to take a simple example, if you look at any search engine, clearly the choices made by the search engine designers are going to impact like my revenue. If I'm selling some objects and I want to make sure I appear on the top of a search result, I don't know what they're using and they won't reveal to me what they're using, right? So there is an inherent challenge here between trying to enforce things when companies have really no incentive to reveal what's the inside of the software. Plus, we are relying on their products anyway because they're well engineered and they work well, right? So that's the trade-off. So I was wondering what thoughts you had about that
Yeah,
angle.
yeah, that's a great question. So yeah, on the first of your questions, resources to look at. So some things I would suggest. One, so there's a conference series that is relatively new that many of you may know, which originally started as a workshop called FATML, Fairness and Transparency in Machine Learning. It then became an ACM conference, FATSTAR, which has been renamed FACT, F-A-C-C-T, although in Google it still shows up under FATSTAR. And they actually, the pages associated with that actually, in the early days, they were quite good at curating a number of resources on this. In terms of papers, some of the references that went by at the beginning of the talk are certainly relevant. One paper that I find useful about sort of grounding this in the sort of existing theory of discrimination law is a paper by Andrew Selds with my colleague Solon Barakis at Cornell called Big Data's Disparate Impact. And I think that certainly started a lot of people sort of thinking on this. More recently, I mean, there's been sort of nice work in the theoretical and pure science community. This paper, Fairness Through Awareness by Cynthia Dwork et al. Was sort of one of the sort of seminal early contributions there. The work I'm talking about here is based in part on a sort of lengthy law review paper that Jens Sendel-Cass and I wrote recently, which tried to also survey some of the literature called Discrimination in the Age of Algorithms. And it tried to sort of come back from within the past year sort of to some of these topics and survey what's known. But yeah, on the question, yeah, it's a very interesting question about sort of procurement. So a lot of this is a procurement question. We want to use an algorithm for, in the criminal justice system, we want to use an algorithm for hiring municipal employees. We want to use an algorithm for deciding, who gets public assistance. I think, right, there's this trade-off that we often think, this is the intellectual property of this company and needs to be kept secret. And that's, I think, in tension with the goal of opening it up. I mean, I think a lot of us, including me, I think, we take the view that, there's a case where we potentially, may need to use regulation to take a relatively hard line and say, if this is something that's having an impact on someone's life, there seems to be some minimal expectation they should be able to examine the basis for the decision. We should then, discuss what does it mean to be able to examine the basis for the decision. But it seems like it's not the right state of affairs if decisions are being made and we can't even tell like why was the decision made. Now there's the danger, on the one hand there's the intellectual property aspects, and again we would point to other domains in which there is a requirement that there be transparency in the decision-making rule, despite the intellectual property considerations. Second, there's the question of gaming. So search engines need to keep their ranking functions secret, because otherwise the system gets gamed. I think there are sort of two things to say. One is, arguably web pages are much more malleable than, say, the kinds of people in the kinds of situations that we're talking about.
Mhm.
The danger with web pages is that almost for free and at enormously large scales, I can sort of create completely synthetic, fictitious web pages that then reverse engineer the ranking function. That's harder to do in the offline world. And secondly, depending on the nature of the rule, and actually my student Manish Raghavan and I have a recent paper about how do classifiers induce strategic behavior, that if I were to say college admissions is based on you having sort of good grades and high test scores,
Mhm.
in a world that simple, of course, if you were to try to game that by obtaining good grades and high test scores, in a sense you sort of delivered on what I actually wanted you to be doing. It's of course not that simple. If you do it through cheating or through sort of idiosyncratic test prep, then that might not be the desired outcome. But I think all of that tells us that when we think about these rules, especially if they become increasingly transparent, we should think about decision criteria that are not only sort of predictive, but also induce this downstream effect that the applicants, when they try to optimize for those credentials, are actually putting effort into the things we want them to be putting effort into. And that's
I
going to be
see.
another important consideration.
Okay. So there was a question on the chat that I want to relay. Let me read it out. It says that there's a question that comes up about auditing code, and the feeling was that somehow, oh, it's too complicated, maybe a little bit simplistic. So auditing code might be something that becomes important. Let me read out the exact
Yeah.
question.
So right. So I mean, again, it's sort of important to say that trying to audit algorithms for bias is going to be an extremely complicated activity. It certainly, I can't stress enough, is not going to consist of looking at the code of the algorithm, because we for all sorts of reasons, we know that's not going to be successful. I really think these are things where, think about what we do in practice. We can probe these like natural systems. I can create synthetic input and I can run it through the algorithm if I have access to the algorithm. I can, vary the input in targeted ways and run it through the algorithm. Right? I can effectively design experiments where the system is the algorithm. I'm designing experiments on top of it. I can also ask people to, run competitions. So a firm might say, we have achieved the optimal trade-off between disparate impact and our objective function, and we could not have done better. One thing you do is run a Netflix-style competition and say, okay, let's take the training data, let's take the objective function and see, can an independent party tasked with the same thing, can they improve on your trade-off between disparity and objective function? Effectively, it's sort of, crucial, something, again, we all know, but is useful to kind of articulate that, when Netflix ran its competition, it didn't say, inspect our code and try to find improvements to it. Even if it weren't worried about the intellectual property, that just arguably would not have been a productive way to do it. They instead said, here's our training data, here's our objective function, try to improve on us. And it lets people build it from the ground up.
So one challenge is that these software systems might know when they are being tested. A good example is the Volkswagen diesel engine
Yeah,
scandal, where it behaved differently on the road and it behaved differently under test conditions.
yep,
So it's just a point I wanted to make. There's another
yep.
question
And
here that I want to read out before we run out of time. So
yep,
this is from Dan Rodriguez from the law school. Disparate impact standards grew out of wider use of testing. Gives an example of IQ testing in employment decision making, a case from 1969. And the struggle over testing continues. And as recently as yesterday, the UC system suspended the use of SAT and ACT scores. So the question is, we have two potential sources of bias at work. One stems from the test itself. Is the test unfair because the questions used? The other stems from how the test would be used by a human decision maker in admissions, and how would an audit regime work to combat these two elements of choice?
yeah. No, those are all great questions. I mean, I should say, of course, universities are considering suspending the use of these in part this year because of the difficulty in students taking them. So there's this extra confound going on at the moment. Right. No, I think actually in a sense, this sort of decomposition of the bias is sort of exactly what we'd like to achieve, and what hopefully algorithms can make more explicit, right? One is the feature I collect, the way this is biased. The other is how that may go into the decision. And I think it's exactly these kinds of questions. At the moment, we see an end-to-end process run by humans, and it can be very hard to say, how do we attribute the gap that we observe to some part in the pipeline? To the extent that the algorithm can disaggregate the pipeline, I think that's useful. And again, I should say that obviously, formal methods are obviously sort of another. I think another interesting direction here is that it doesn't have to be purely a kind of black box testing of the code, but I think there's a very interesting opportunity for sort of, to the extent we can make sort of formal guarantees about algorithms. I think that also can play an important role in all of this.
I see. So when you were talking about bias, the question I sort of thought of with the groups A and D, I think you used towards the end of the talk. So one could argue that SAT scores, for example, could be perhaps artificially boosted by going through some practice or training sessions. And then students who can afford that might get higher SAT scores than students who cannot.
Yeah.
And so when you just see a score, you don't even know perhaps who went through a training for this or not, right?
This is part of the challenge. I mean, I think, sort of phrased in a kind of computer science terms, there's a latent variable, or statistical terms, latent variable I'd like to estimate, which is your capacity to succeed in college, and suppose that's what I believe I truly care about. I don't get to directly observe that. Instead, there's something interposed between me and that variable, and that's the test score.
Yeah.
Now, the test score is a noisy signal emanating from that variable I care about. And so I have these two applicants, one of whom had lots of test prep, lots of practice, another whom went to school, under more challenging conditions. And, so now, one gets a 1300, one gets a 1280. If I think of these not as just absolutes in themselves that are the true basis of my decision, but as noisy signals from a latent variable I'm trying to observe, I might say the one who achieved that under, more difficult conditions, that's actually a signal that that latent variable is actually stronger. And so I think, when we think of these as noisy signals rather than the measure, the sort of end properties in themselves, I think that's sort of useful in trying to think about how we ought to be using these.
I see. So it is exactly one. So let me maybe stop the questions. And some of the questions are from faculty who you'll be chatting with this afternoon anyway. So I'm hoping that they can ask you then. But just to quickly recap the game plan. So you have some time off now, John, to get some lunch. And then starting around 2, I think you have an email from Pam, which gives you the code for the meetings in the afternoon. So thank you again very much for your talk. Thanks for taking the time. And I'm glad it was such a huge draw, perhaps even a bigger draw than it would have been on campus.
Well, thanks very much.
These are hard to
Glad,
predict.
yeah, no, and thanks everyone for coming and taking part in this. And
yeah, great. Thank you.
Glad to have done this.
Bye.
Thank you. Bye.